Fractional dimensions. Imagine the possibility that the universe, at its most fundamental level, isn't simply defined by whole dimensions, one-dimensional lines, two-dimensional planes, or three-dimensional spaces, but rather exists in the enigmatic realm of fractions. Today, I'll take you into one of physics' most tantalizing theoretical landscapes, fractional dimensions. Get ready, because this will challenge the foundation of how we interpret space and reality itself. Let's begin with a question that at first might seem philosophical. What is a dimension? To a physicist, dimensions are degrees of freedom, the fundamental ways objects can move or exist. In our everyday experience, there are 3 spatial dimensions and 1 additional dimension of time, making a total of 4 that we often refer to as spacetime. But have you ever pondered, could there be something between these dimensions? Could spacetime subtly interpolate between one-dimensional and two-dimensional? Let's push deeper into the brilliance of fractional dimensions. Here's where the magic starts. The idea of dimensions as fractions is precisely what fractals have been hinting at for decades. Think of a jagged coastline or a tree branching pattern. From afar, we can generalize them into 2 dimensions. But if you zoom in on the shoreline or the tree indefinitely, their features never resolve into something smooth. They retain a complexity hinting at dimension fractions, something between 1 and 2. These are called fractal dimensions. But how does this idea apply to fundamental physics? Let's venture into quantum mechanics, where fractional dimensions might redefine the most enigmatic phenomena. Could the behavior of particles, their wave-particle duality, or even their probabilistic existence, be fundamentally explained by fractional spatial frameworks? Some researchers delve into this idea by combining quantum field theory with the mathematical structure of fractional calculus. Fractional dimensions aren't just an abstract mathematical toy. They may affect our understanding of gravity. In Einstein's general relativity, space-time curvature happens because of mass and energy. What happens if space-time itself bends differently in fractional geometries? Think of it like this. Gravity, which we perceive as consistent within 4-dimensional space-time, might take on new patterns at scales where the space-time dimensions deviate ever so slightly from an integer. This fractional deviation could hold the key to phenomena like dark energy or the missing mass of the universe we attribute to dark matter. I can hear your questions already. Is this purely theoretical, or can it lead to testable consequences? While experimental evidence in this domain is sparse, evolving technologies offer glimpses into fractional geometry's observable effects. For example, there are hypotheses suggesting fractional dimensional phenomena could reveal themselves at the Planck length, where space itself is quantized into minuscule discrete patches. It's as if space-time, rather than being a smooth fabric, might resemble a fractal tapestry at the smallest scales. Let's not overlook black holes. Fascination surrounding them often boils down to the singularity where everything collapses and physics seemingly breaks down. Could fractional dimensions provide a mathematical escape hatch to bypass the mysteries of singularities? Picture this. Fractals create a dimensional transition zone where infinities don't exist, but instead, transitionally fractional-sized realities smooth out the inconsistencies. This could redefine theoretical cosmology. Another fascinating proposal intersects work in condensed matter physics. Systems like graphene or quantum materials sometimes display dimensionalities that feel halfway between integer values. Researchers use fractional mathematics to predict and explain specific quantum states in these systems. If condensed matter can manifest fractional geometry physically, could similar principles govern universal geometry? By now, you might sense how different disciplines intertwine here. These concepts aren't isolated. They link quantum mechanics, materials science, cosmology, and even fundamental theories seeking quantum gravity. This interconnectedness is what fuels optimism in their transformative potential. Of course, we should remain reflective. Speculation in untested territories is a physicist's intellectual playground, but also requires grounded honesty. Fractional dimensions may converge with established models, perhaps tweaking physics as we see it. or may fade as merely elegant mathematics unrelated to our universe. The beauty lies in the exploration itself. Leaving theory for a moment, think how fractional dimensions touch upon philosophy. Is dimension itself possibly not fundamental, but emergent? Could human perception of dimensions create an artificial ceiling on our understanding? This notion belongs to radical openness, being able to discard rigid forms of comprehension if something more nuanced holds deeper validity. The practical applications of these ideas could drastically alter physics. Imagine solving problems like the smallness of the cosmological constant, or mapping extreme physical states, such as those in neutron stars. Even computing could benefit by mimicking fractional dimension-inspired resolutions for solving previously intractable problems. So now, let's step back briefly. If fractional dimensions hold any solid truth, they fundamentally reconstruct the stage for understanding both microcosmic and cosmic phenomena. It speaks to spacetime's plasticity and challenges us to shift our paradigms. For a long time, we've clung to four-dimensional universes. Here's your push. Forget cubes, forget grids. Instead, envision reality as a fractaled whisper. Here's my question to all of you intrigued physicists. Do you believe fractional dimensions integrate into our universe, or do they remain mathematical abstraction? Please share your nuanced perspectives and thoughts below. I hope today's deep dive into fractional dimensions has sparked your imagination to see space-time beyond integers. Thank you for joining me on this intellectually rigorous journey. Until next time, keep questioning, keep exploring, and let's hyper-focus on the unknown realities together.